Hello everyone. Today we will be discussing about the session Data Editing in GIS. In the previous session we have studied that how we are inputting the data sources in GIS. So in that case there can be certain editing that occurs or that requires during the GIS analysis. In this session, we will be going into detail of how data editing occurs in GIS. In this session, we will be dealing with what is data editing, what are the common errors that occur during the data inputting in GIS, and what are the methods of such type of error rectification. So, during the process of encoding, many errors might be occurring in GIS. There may be errors in coordinate data as well as inaccuracies and uncertainties in attribute data. A good practice in GIS involves continuous management of the data quality by identifying and correcting such type of errors in the data stream. Hence, before successfully using the method of data analysis, it is better to correct these errors before they contaminate the entire GIS dataset. And this process of detecting and removing errors through editing is termed as data editing or data cleaning. Let's look into which are the common type of errors that occur during the data inputting in GIS. The common errors are classified under three groups: an entity error, an attribute error, and an entity attribute error. An attribute and entity error occurs individually in both raster and a vector-based GIS, whereas in case of an entity attribute error, it happens only in a vector-based GIS. So, the data editing or the data cleaning generally occurs under three stages. The first stage is to detect and correct the error. The second stage is the data reduction and generalization process, and the final stage is edge matching and rubber sheeting. We will be moving into each stages in detail. The first stage of detecting and correcting errors. There are three major sources from which an error in the input data happens. The first type of error occurs from the source data itself, and it's very difficult to identify such type of errors because most of the errors occur at the time of surveying or at the time of printing. The second type of error occurs during the encoding process that we already discussed. We know different types of encoding process like keyboard entry, manual digitization, automatic digitization, and so on. So, there can be a chance of typing mistake during the keyboard entry, or there can be a wrong digitization occurs along a line. So these type of errors are classified under encoding process. And the third type of error generally occurs during the data transfer, construction, and conversion. As we are converting different sets of data between different formats, this leads to loss of data. Which are the common errors that occur in the attribute and the spatial data? If you look into the case of an attribute data, the errors are relatively very easy for us to spot. We will be able to spot it with the help of manual comparison from the original data. At the same time, the error in a spatial data is often difficult to identify and correct. Such type of errors will come in many forms depending on the raster or the vector model we are using and the method of data capturing. Which are the common methods of attribute data correction? First one is an impossible value. Here, I will be explaining with the help of an example. Consider one of the southernmost state of India, that is Kerala. The state receives a very high rainfall during the monsoon season. In case of a negative value that occurs in the rainfall in Kerala during the monsoon season, means it can be a chance of an impossible value. That means a simple check for an impossible value can be found when a range of data is known. Here we already know that a region with a heavy rainfall, there can be an impossible, or it can be impossible for that region to have a negative value in the rainfall during a particular season. So this can be checked with the original data. The second type of attribute data correction is extreme value. Here also I am citing the example of Kerala, the region that receives heavy rainfall to 12 to 30 centimeter maybe in a day during the monsoon days. At the same time, if a value in the GIS data inputting is showing 125 centimeter of rainfall in a day, means it should be verified. It is more likely to be 12.5 centimeter rather than 125 centimeter. So such type of extreme values can be cross-checked against the source data for verification. The third type of attribute data correction is the internal consistency. If the data received from a statistical table, means we can make a cross-check against the summary statistics provided with the source document. Scatter diagram is another method of attribute data correction. If we are having two or more variables in an attribute data, we can make it for a correlation. And while correlating the variables, we always plot in an XY axis. And if the value is departing from the regression line, it needs to be verified. Trend surface is another method of correction. Trend surfaces are generally used to highlight points with values that depart from the general trend of the data. Again, I am citing the example of rainfall pattern in Kerala. The region receives high rainfall during the monsoon and less rainfall or very low amount of rainfall during the summer season. But if the value is showing a high rainfall during the March, which is a summer season in Kerala, means it requires an investigation because it deviates from the general trend of that area. What are the common errors that occur in the spatial data? The first one is that of a missing entity. We all know that polygon have always a closed entity, and hence the boundary must be continuous while encoding. If the polygon is not closed during the encoding or during the digitizing by missing the connection between the points, this will create an error which is known as missing entity. Here, look at the diagram below. It shows a missing entity. The diagram shows a region with a polygonal structure. That means that always the line should be continuous and it should finally meet at the original entity. But what happens is that entity is not being closed, and that entity we call them as, or such type of error we call them as a missing entity. Next is a mislocated entities. Sometimes the point or the line entities are digitized by the operator in a wrong place. We call them that it is a wrongly placed or a mislocated entity. Missing label. Some polygons or line or point entities are unidentified and not entered with actual spatial data. Here again, you can look at the diagram that a feature, maybe a pond or some feature is being depicted in that ward 1, at the same time there is no spatial reference given to that entity. It is a missing label. In case of duplicate label, what happens is that there may be 2 or more identification label found for a single entity. Towards the bottom of the diagram, you can see in a triangle shape icon that 2 entities are being shown, or 2 features are being shown, and they have same label point. So that is a duplicate label. Pseudonode is actually not an error. Sometimes a single line connects itself and there are only 2 arcs, one in the beginning and other in the end. What happens is that a pseudonode or a node will automatically come in between these 2 nodes. And such type of node we call them as pseudonode. In the picture you can see in the top right corner a pseudonode, that there is a node that connects the ward 1 and there is a node that happens in the ward 2. Between the node there is actually no node there, and these 2 nodes are connected with a straight line. So what happened is that when a straight line continuously occurred, automatically a node appeared in between the 2 nodes, and that we call them as a pseudonode. It do not indicate as an error. Dangling nodes are generally unconnected node of a dangling segment. Here again in the bottom of the diagram you can see a dangling node. What happened is that one part of the node has been connected, whereas the other part was not connected with the polygonal area. So that part or that node has not been connected with the rest of the feature. We call them as a dangling node. Noise are generally irrelevant data that occur during the digitization process or during the scanning process or during the data transfer. Duplicate entity is a common error that occurs in a spatial data. It generally occurs when 2 or more identification labels, it generally occurs when the polygon entities that have been digitized twice in case of a common vector boundary. This is a very important case. I will be explaining here again with the diagram that there are 2 wards here, ward 1 and ward 2. And the ward 1 and the ward 2 is connected by one boundary, common boundary. What happens is that while we digitizing the ward 1, we are digitizing that entire boundary. At the same time, while we digitize the ward 2, that boundary is again being digitized. That means that we have digitized a common boundary twice. And we call such type of entities are duplicate. These type of duplicate entities create 2 types of errors. One is a silver and other is called gaps. What is a silver? Look at the diagram here. In the diagram, it shows an area or a plot. In that plot, some areas have been shaded and some areas maybe we can consider them as a road or a common boundary between the other plots and all. What happens is that towards the top right corner, there is a plot that has been shaded, and near to that plot some road or some polygon is being located. What happened is that while the operator has digitized that polygon, some area of the unshaded portion has also been included in the shaded portion or the shaded plot, and that overlapped. That means the area that has been shaded has overlapped some of the area which is not shaded, and that shaded portion we call them as silvers. So silvers generally occur when an adjacent polygon apparently overlaps the other polygon. In case of a gap, the apparent space between the adjacent polygons will occur. So what happened is that they have missed out, or the operator has missed out in digitizing a few area of the plot, and this has created gap. So filters and gaps are very important feature, or very important, or the most common error that occurs in a GIS dataset. What is an undershoot and overshoot? Both are contradictory to each other. An undershoot generally occurs when every segment begins and ends at a node point for a polygon entity. If not closed properly, it is an undershoot. So here I have circled that feature in the diagram, that in a polygon we know that it should be always enclosed, but sometimes due to our mistake we may not have enclosed that polygon, and that portion we call them as undershoot. And overshoot is just opposite to that of undershoot. What happens here is that the segment has been digitized past an intersection. So already the intersection occurred in the given diagram, but the digitizer or the operator has further digitized some more entity above that enclosed area. We call them as overshoot. How you can correct such type of errors that occur in a spatial data? Most of the GIS packages will provide suitable editing tools for identification and removal of error in vector data. Corrections can be also done interactively by the operator on screen or automatically by the GIS software. If we visually compare the digitized data with the source document, it helps to identify obvious omissions, duplications, and wrong additions. Some digitizing softwares can correct systematic errors like overshoots automatically. In case of a raster data, the missing entities and noise are the major errors or the problem. In an aerial photograph, if you take it as an example, noise occurs during the rainy season due to high cloud cover. This makes it difficult to get a clear image of the ground feature. This noise often shows up as a scattered pixel. There, the attribute value is not conformed to its neighboring pixel, and this form of error can be removed by a process known as filtering. So I will be here mentioning what is a filtering process. It is an analysis technique to find the values of a scattered pixel created by the noise. How the filtering will work? It involves passing a filter over the noise dataset and recalculating the value of the central pixel from the value of other pixels within the filter. But this technique requires some carefulness, because the genuineness of the feature can be lost if the filter is being used at a large scale. So remember, filtering process is always suited for a small scale feature, not for a large scale feature. So what all actions we can undertake for such type of errors? In case of a missing segment, we can either draw it or connect it by digitizing process. The gaps can be rectified by indicating which arc to be extended or which node to be moved. If there is an overshoot occur, we can delete the node that needed. And in case of an undershoot, we can merge the nodes or extend the segment and remove such type of errors. So here a diagram is showing that what happens or what are the common artifacts during the digitization process and how it has been rectified or the corrected data after the error rectification. The second stage is that of reprojection, transformation, and generalization. Once the spatial and the attribute data have been encoded and edited, it is necessary to process these data geometrically to provide a common framework for the reference. The scale and the resolution of the source data is also needed to be taken into account while combining data from a range of sources to a final integrated database. Here comes the role of reprojection, transformation and generalization. Hence, reprojection, transformation and generalization are important factors in data stream. What is a reprojection? I already told you that we will be deriving the data from maps, from different projections, different sources and all. Hence, it is necessary to be reprojected into a common projection system before being combined or analyzed. If not reprojected, the data derived from a source map drawn on one projection will not plot in the same location as data derived from another source map having another projection system. Here, I will be citing an example. For example, consider the case of a coastline that is being digitized from a navigation chart, and you know that the navigation charts or the most of the navigation charts are prepared on the basis of Mercator's projection. And if that type of chart is combined with a census boundary of a region digitized from a map drawn under the Albers equal-area projection, then the census boundary along the coast will not plot directly on the coastline because both are from different projections. The next stage is transformation. The data derived from the different sources in GIS have different coordinate system with different units of measurement, origin and orientation. Hence, it is necessary to transform the coordinates of each of the input data set into a common grid system. This involves some type of linear mathematical transformations and some methods like translation and scaling, creating a common origin and rotation. What is data reduction and generalization? In GIS, the data may be derived from maps of different scales, and hence GIS input may require data reduction of various kinds. A simple way of data reduction is to average the measurement of a single value and enter the average into a database. However, a complex form of data reduction involves two options. Either we have to accept the level of details and incorporate all the larger data than what we actually require. The second option is to develop a less precise representation from the original source data, and this process is known as generalization. Thus, if the source map of different scales have to be used together, we have to generalize the map to compare a large scale map with a smaller scale mapping source. The simplest method for generalizing a vector data is to delete points along a line at fixed interval. For example, we are deleting every third point or every fifth point. However, this technique will not preserve the shape of a feature. It will get distorted. Another method of generalization is to consider a locus of points, then reduce the total number of points in the vector data and reduce the level of details in the dataset. Most common numerical algorithm like Dolga-Speckwer algorithm is used for such type of generalization. For continuous raster data, generalization is done through two steps. First one, we will compute the average value of the attribute in a 2x2 neighborhood. Then we will record this average value in a new raster cell. That raster cell will be having a geographic location shared by the original previous 4 raster cell, and this process is known as resampling. Here I have drawn an example to show the generalization. In the beginning you can see that how many points are there. Such type of locus of points have been reduced in the second stage, like that till how much we can reduce, we will be doing it in the process of generalization. It is the main problem associated with this is that the original shape may be slightly distorted in generalization process. The third stage is that of edge matching and rubber sheeting. When an area of study is extended over several map sheets, think that we are studying about an area that will be covering n number of topo sheets. It is common that in the beginning each map have to be digitized separately. We cannot do it everything simultaneously. So what we will be doing it, all the maps will be digitized separately and later on it will be joined together. This joining process is known as edge matching. Normally, when each map sheets are joined after editing, reprojection, transformation and generalization, small mismatch will occur between the adjacent sheets. Here I will be showing the difference before an edge matching and after an edge matching. What happens here is that when two map sheets, that is the sheet 1 and the sheet 2 has been joined, there some small mismatching occurred between those features. You may not be able to see that the road is a straight line. There is some difference between the sheet 1 and sheet 2. They have not joined correctly. Similarly is the case of stream and the case of pond. They are not showing it as a complete polygon. So what the edge matching will do? It is a process of operating on one or more than one tile at a time to ensure that there is a correct match that occurs between the two tiles for that entities that will extend across the boundaries. So the process of edge matching involves three major steps. First one, we will be resolving the mismatches at the sheet boundaries. So now a mismatch has occurred between the road for the stream as well as for the pond. So we will be resolving such type of mismatches and they will be joined together. The second step is that the topology of the joined coverage will be rebuilt. Here the topology should be rebuilt because as new lines and polygons have been created from the segment that lie across the map sheet. And the third stage is that the redundant sheet boundaries must be resolved. Here what happened is that we are able to exactly delineate between sheet 1 and sheet 2 here because we can see a straight black line between the sheet 1 and sheet 2. But once the edge matching happened is that there you know that our features are being joined together. Those area, the part of our feature will be hidden if that sheet boundary occurs between these features. So those sheet boundary will be resolved slightly and or dissolved where the features are enclosed or continuous. So this is about edge matching. And we are moving to the last stage, that is rubber sheeting. Certain data sources may give rise to internal distortions within the individual map sheets. These distortions generally occurs in an aerial photograph. You might have already seen that in aerial photographs there will be cloud coverage or some distortions. Why? Because the aircraft is continuously moving and the distortion can be caused by the movement of the camera lens. These type of inaccuracies remain even after the transformation and reprojection process. So such type of problems of internal distortions within the map sheet are rectified through the process of rubber sheeting or conflation. Conflation involves stretching the map in various directions as if it is drawn on a rubber sheet, so that you can stretch it to different directions and make the shape of that feature correct. So what happens here is that in the diagram you can see that the original boundary or the original image that we got is a continuous one and a dotted line represents the final rubber sheeted boundary. So what happens is that the object on the map that is already correctly placed, we keep it safe down. We will not change those type of features that are already correctly placed, but there will be some mislocated and wrongly shaped ones. Those features we will be stretching it to fit with the control points. How we will get these control points? They are the known points that are already identified on the ground and on the image we have given, or we are comparing that with the original image. So in that way we will be changing, or we will be always keeping the correct points fixed without unchanging them, and we will be only moving or rubber sheeting those areas with to the control points so that its shape will be almost preserved. And this is way a rubber sheeting will work. So with this, the common errors and data editing in GIS has an end. We will just go through a quick glance of what we have seen today in today's session. Data quality is an important factor in GIS. We should always correct such type of errors before an analysis taken place. The common errors that occur during the data inputting are the entity, attribute and an entity attribute error. And the process of detecting and removing such errors through editing in GIS, we call them as data editing or data cleaning. And the data editing generally has three major stages. First, we will detect and correct the errors. Then it will be followed by transformation, reprojection and data reduction through generalization process. And finally, we will match the edges between the sheets that come across several map sheets. And finally, we will reduce the distortion of the shape and will try to preserve back the original shape through the process of rubber sheeting. So I hope you understood this portion. I wish you to have a nice learning. Thank you.